In a previous video, somebody asked in a comment, can you make a FreeCAD tutorial on a planetary gear train? So yeah, I can do that, no problem. It's not going to be exciting, but it will be informative. The steps are really, you got to know like the size of your gears and the tooth counts for the planetary gearbox before you get into FreeCAD. So the first step is to make an Excel file and fill in some stuff and calculate some values. And then take those numbers and just feed them into FreeCAD. It's actually pretty painless. We'll probably just skip the intro and get right into it. I'm Josh Whitman, CEO of Whitman Technological. We need to know some things about the gearbox before we try to pop it into FreeCAD and actually make some gears, right? So if you've got, let's say we've got a ring gear, we'll do some really nice artwork here. Let's say here's our ring gear, right? And oh yeah, I'm really good at this. Okay, so you got a ring gear, right? And then you have a planet. And another planet on the other side, and then a sun gear, right? A nice blue sun. That makes sense. Okay, so with the ring gear, the relationship between the teeth is the ring gear teeth count equals the sun gear plus the planet gear on both sides. So 2 planet gears plus the sun gear equals the number of teeth for the ring gear. So if you had 100 teeth here and 50 teeth here, that would leave 50 teeth left. And between these two, that would mean 25 teeth per planet gear. So knowing that relationship, let's start with teeth. And we're going to say ring, sun, planet. And if we just choose an arbitrary number like 100 teeth in the ring gear and 50 teeth in the sun gear, the planet gear equals the ring gear minus the sun gear. And it's this number divided by 2, right? And that's how many teeth we have. So if we have a ring gear, now you can do cool stuff with a just a single planetary gear. But what I'm building is a compound planetary gearbox. And so that's 2 planetary gears that work in concert with each other. And so we have a second planetary gear that also has ring, sun, and planets. Now, the thing about a compound planetary gear is the planets have to line up with each other. You can't have a planet here and then a planet that is here or farther out. They have to have the same center because they rotate about that axis at the same time. So our planet gears have to be equidistant. Now for a if we have the what would this be called? The radius of engagement, like where the gears, essentially what their offsets would be if they were meshed properly with each other. So where is that line from the center of a gear? So if we said gear radius, and that's calculated as, let's see, how do we do that? It's the size of the teeth. Okay. So before we get to this one, we need, I guess, yeah, let's see. We're going to need module. And that's the gear tooth size. All right. So the tooth size defines, let's see, wrap text. Okay. Oh, we're going to start to mess up our amazing drawing here. So let's cut, and paste. Let's move this elsewhere. Paste. Paste. Okay. I don't know why it wouldn't let me choose paste from there. Okay. So our module, can we hit something like Shift Enter? No. Okay. Looks great. So far, so good. Okay, so here's our tooth size, and this is defined by our 3D printer, right? Or at least in my case it is. I can only print teeth that are like 0.8 is like the tiniest teeth I could print, and that's way too small. So we want like a 1.6 is good. 2mm teeth are really good and chunky and feel strong, in my opinion, coming out of my printer. So the minimum tooth size that you might want to work with can vary quite a bit. I can do 1mm teeth, and I would rely on them in some situations, but 1.6 is a great tooth size, so we're going to work with that, and that helps us define the gear radius, which is going to be the tooth size, I think. Let's see, the tooth size times the number of teeth divided by 2 gives us the radius. The diameter is the tooth size. So we got ring, sun, and planet again. What happened? Oh, no. Oh, okay. Escape. Whoops. There we go. Okay, ring, sun, and planet. So our ring gear equals the tooth size times the number of teeth divided by 2 to get the radius. And if we make the tooth size a standard one, then we can get, so now we have a ring, sun, and planet, and these make sense because it is half and then half again. And if we do the same thing here, we get, and let's see, that's F19, but that's F20, so we want this to be F20, like that. So if we have 2 stages and they have exactly the same number of teeth and the same tooth sizes, well, these planets are going to line up, and everything will be exactly the same size. So if you turn the center, the planets will rotate at the same speed, and the outsides will rotate at the same speed. So it's basically like a drive shaft. There's no reduction. It's a 1-to-1 ratio. So the cool thing about the planetary gearbox, so then we have one more thing. Distance to planet, right? Dist to planet. And that's going to equal the sun radius plus the planet radius. So the distance from the center of the sun to the edge of the sun, and then from the edge of the sun to the center, or from the edge of the planet to the center of the planet, and those are meshed together. So this is where the axis of the planets is located. So as the planets are rotating, they're rotating 60 millimeters from the center of the sun gear. So we'll also copy that to here. And so for a compound planetary gearbox, that central axis of rotation for the planet gear has to be in the same place. So when we start changing these teeth counts and we start modifying the second stage to be different from the first stage, so we get something other than a 1-to-1 ratio, this is the critical thing that has to be equal in order to make a compound planetary gear work. So now we take our ring gear, and we're going to go with 4 planets, right? That's our number of planets. So you want to work with multiples of 4 generally. If we say 100 and then we say 96, that gives us 23 teeth here and 25 teeth here. And now we can see, these radiuses, the radii have changed. And then we see that, look, this is smaller now. It's no longer rotating about the same axis. This one's going to be offset a little bit. And to adjust for that, we say 1.61. This is my super low-tech way of figuring it out. So 1.65, 1.63. Like, there's math to do it, but my 3D printer is only accurate to within, like a 1/10 of a millimeter or maybe a 100th of a millimeter. So 635 maybe. So all we got to do is find the tooth size that gets us to where this is close enough that our manufacturing equipment can't even deal with those precisions anyway, and then we're ready to go. So this is still too low, 1.637. We're 1.64. 1.64. 1.645. Okay, 1.644. And look, that gets us to within, that's tenths of a millimeter, hundredths of a millimeter, within thousandths of a millimeter, 6 thousandths of a millimeter, it's equal. So so if we say 3.9, right? And now we're really close, 3.8. Yeah, so between 3.8 and 3.9, right? So look, we're so close that our equipment would not be able to make a distinction between these values. It can't manufacture to this level of precision. So this is as good as it gets. We've just created a valid set of gears, and we know the tooth sizes needed to make a compound planetary gearbox where the planets of stage 1 and stage 2 are the exact same. The axes will rotate. The axes will rotate at the same distance from the center. So given this stuff, we can then hop into FreeCAD and we'll make a new file. And you're going to need, let's see where it is. It's somewhere in like preferences, work stuff. No. Wherever the workbench is. Toolbars. There's like a add-on manager. There we go. That's what it is. So you're gonna need the gears one. It's so good. You have to have gears. Where's gears? I think it's called FCGears. FC Gear right here. That's the one you want. You're gonna need FC Gear. That's super cool. Okay. So right off the bat, we start with FC Gear. It's just called gear. Okay. We're going to make a regular spur gear. And now we have our information from here that we're going to do. Let's start with the sun for stage 1. It's got 1.6 millimeter teeth and it's got 50 teeth. So on this gear, we say, now it's going to be a double helix. Well, let's see. Let's get 1.6. Modules are 1.6 and teeth is 50, right? So this thing's huge, of course. I'm not making something that I'll be able to 3D print, but you just change the teeth counts. I ended up with like 64 teeth with modules of 1.6 for a really big gearbox. For this gearbox, this has 64 and 68 teeth, and the outer rings, and 24 teeth on both planets, and then one sun is, this one's probably this one's 16 teeth and 20 teeth. So those are the numbers I used for a gearbox of this size, with modules that are 1.6 and slightly smaller than that for stage 2. So just so you have a rough idea of how it comes out physically in the real world. So we're going to make this a double helix, and we'll set a beta of, say, 15 degrees. And that's going to give us a nice little herringbone pattern. And we're going to set the height to be like 20. And the nice thing about this double herringbone is that when you assemble the gearbox, you'll need to put a little notch, a little cut into the ring gear so that you can open it, get all the teeth packed in and close it back in and kind of shuffle it to get the teeth just right. And then you usually put a collar around the outside of it to keep it from expanding and skipping teeth during operation. Okay, so there's our first sun, right? And we'll rename this to stage 1 sun. And then we're going to make another one. And so this will be, we'll do the same thing with the double helix at 15 degrees and a height of 20 with modules of 1.6. And what are our tooth counts are going to be 1.6. The planet is 25. Okay, so this is going to be, teeth is 25. And then I think that's it. Do we just have to recalculate? There we go. Okay, so there's our sun and stage 1 planet. Okay, and then we need our stage 1 ring, which is going to be, so we can turn off those. And now the ring has modules of 1.6, tooth count of 100, and then it is also a double helix with 15 degrees and a height of 20. Okay, so now we've plugged all this stuff in, and when we run this one, we're going to end up with so there's the inside of the ring gear, and actually there's some settings here for I don't know. I made the last ones a while ago. Reversed backlash. I feel like there's one for if it's an internal, but I don't see it now. It's there somewhere. If you look in the documentation, it's there. Maybe undercut or something. Yeah, it might be undercut. At any rate, so once you've got this, you'll actually need to subtract this gear from a cylinder or something. Oop, I made it mad. There we go. Okay, we go to part. And we'll make a cylinder. And the cylinder has a radius of, let's see, we got 160, so like 170. No, that's the radius. We want half of that, so if you could divide by 2, perfect. Height of 20. Now, subtracting where the heights are exactly the same is not great, so we're going to go height of 19.999. 998. And we're going to do a placement on the Z of 0.001. So that way it's just slightly above the bottom and below the top. And now we can take our cylinder and our gear, and we can subtract the gear out of the cylinder. There's a couple settings in the gear. Yeah, for 3D printing, you can set like backlash and stuff that will let you put a little bit of extra gap between the teeth, so that when you're printing, if your printer is adding a tiny bit of volume to the teeth, like to the tune of micrometers of volume, you actually do want to account for that. So now we have a nice ring gear, and if we take our sun gear and then we take the planet gear, and now we know that the distance to planet is 60 millimeters here. So we can just move this on the x-axis, 60 millimeters, and now you've got, you know, nice tooth engagement. We might want to rotate this by like 1 or 2 degrees or something, just to get the teeth to line up. So we might, okay, so now it's meshed well with the, one of these needs a -15, right? See how these, they should be pointing to each other. Let's see. If, so these look good where they're both pointed the same direction, but these are pointed towards it while these are pointed away, which means they're going the wrong way. So the sun gear, instead of a 15-degree beta, we need a -15-degree beta. And then we should see the teeth. Yeah, so now they're pointing in the same direction, you know, where the V of the tooth here. They're both pointing in towards the enmeshing of the gears. And if we go to the other side, they're both pointing out of the enmeshing of the gears. And it'll be the same over here, where the V that the herringbone makes here and here are both pointing in to where the teeth are enmeshing with each other. So now we can see we've got really nice engagement. Everything looks really cool. We can take this planet, we can copy and paste it a couple of times, and then we just change its placement from 60 to minus 60. Right, this is by no means a comprehensive tutorial, but this is how I did it. And then we say 60 there, and we say minus 60. Yep, that's way too far. And 0. And there we go. And then we can, as needed, we might have to rotate these so that the teeth are lining up properly. You know, so we should. So these never quite line up, and that could be because I chose 25 instead of something divisible by 4. Yeah, so that's a bummer. The rule of thumb is that the teeth counts should be divisible by the number of planets that you have. And in this case, we could almost do 5 planets. I don't want to try that, but we could. So because everything's divisible by 5, but then we get 23, right? And that's where the issue would then come into play. So if we did, what we'd want to do is like 102, and then 52, 48, 44, 40, 36. We're fighting a losing battle here. 104 and 36, 40. There we go. Okay, so 104, 40, and 32. Because 32 is divisible by 4, and these are also divisible by 4. Is that? Yeah, 26 times 4. Yep. Okay. And then, so we want to do the same treatment here where we say, so the ratio, like there's 4 planets in our final gearbox, right? If you had 6 planets or 10 planets or whatever, then you want the tooth counts to all be divisible by 10 or 6 or however many planets you have. We're having 4 planets, so everything needs to be divisible by 4. So if we say we've got 104, and then let's say we do 108, and our sun has 44, that gets us 32, but this should be okay. Right, so then we've got 57, 1.6. Yeah, okay, good. So this will work because everything's divisible by 4 here. So the sun ring and planet gears will all be able to mesh into their teeth properly at like an evenly distributed angle, you know, where it's like 90 degrees apart where each planet is positioned relative to the other planets. Okay. So let's adjust the modules again. 1.5 gets us really close. 1.51, 1.52, 1.518, 1.515, 1.517, 1.516, 57.608. I'm satisfied with that. Okay. So let's go fix this mess. So we're 57.6 is our distance. We have 104, 40, and 32. So at this point, you guys are probably like, "Oh, this is torture." It is torture. Making these things, you gotta do a lot of stuff. Okay. So our tooth counts are gonna be: the ring is 104, the sun is 40, and the planet is 32. The sun is 40. The ring is 104. Our cylinder needs to be just slightly larger in radius, so let's say 90. Doesn't really matter because this is just for demonstration. Let that recompute. There we go. Okay, now we take our planet, and this has 32 teeth. Meanwhile, does that look insane to you? Let's put the right number in and see how insane it looks. Meanwhile, it is only 57.6 from the center. So we go over here to position 57.6, and now we can rotate it a little bit. See if we can get the teeth to mesh up. Oh, that's right. Okay, so we rotate that, and then we go to the sun, and we rotate. Oh, and then we go to the sun here, and we rotate the sun. Give or take just enough that the teeth are obviously enmeshed with each other. Now we can remove these ones, and we'll make a copy of this. Its position will be minus that. So it's over here, and you can see the teeth line up. Now, because it's divisible by 4, we should be good to go. We'll do another copy of that. And instead of that, it's going to be on Y. It'll be 57.6. And we can see the teeth are meshed up there, just the same as they're meshed up here. And that looks really good. We take the same thing here. So yeah, being divisible by the number of planets is going to be kind of imperative to making it the teeth actually mesh up with each other. And now we can see the teeth are enmeshed more or less exactly. I don't have it like perfectly dialed in across everything, but all you do is just rotate these ever so slightly by less than a degree until eventually they were perfectly aligned with each other. So there's stage 1, and then we go back to gear, and we're just gonna hide all of that for right now, and we're gonna add all the second stage of gears. So we're gonna take these, and we're gonna say for the second stage we're working with 1.516. We have 108, 44, and 32. So beta of 15. Height is 20. 1.516. What? 1.516, and okay, so kind of there we go. 108. So if we compare that to the ring gear here, you can see it's just ever so slightly a different size. It's just a tiny bit smaller, and that's perfect. The closer they are, the higher the gear ratio, like 300 to 1 or something. You can get crazy high gear ratios with a single compound planetary gearbox. So that is Involute Gear 006. We take that. Oh, it's a double helix. And then we'll do the same thing with the cylinder. So we go over to part, and we make a cylinder, and this cylinder is 19.999. Has a placement on the Z of 0.001. Oh, 19.998. Sorry, there we go. A radius of we'll say 190. Oops. Of 90. Yeah, that looks good. We could even come down a tiny bit. Yeah, something like that. And then the Z. Oh, 1 micrometer. Okay. I thought that got messed up. Now we take our cylinder and our gear, and we subtract. And this gives us the ring gear for stage 2. Slowly but surely. There we go. Okay, there's the ring gear for, so if we look at the stage 1 ring and the stage 2 ring together, you can see they're just the tiniest difference in size and the gear placement. You can see they're ever so slightly out of phase with each other, which is perfect. We're going to get a really high reduction ratio. We'll get a ton of torque out of it, and we'll slow it way down, so you can pipe a fast motor into it, and you'll get a lot of torque out of it. Okay, so there's the ring gear, and then we go over to gear, and we've got the sun gear. So here's the sun gear, has an angle of, did we determine the sun needed a minus 15 in the first one? Oh, that's the wrong place for an angle. 0 is good there. Oh, I'm not even in that. There we go. Wow, none of this looks right. Okay, beta is minus 15. The double helix is true. The module is 1.516, 44 teeth. 1.516. Teeth is 44. And then that's cool. That's all good. Oh, the height needs to be 20. Height is 20. Okay. And then this is S2 sun. This one here, S2 ring. This one here, S1 ring. Okay. And finally, we add our planet, our S2. Oh, it's hiding inside the other ones. Okay. Beta of 15. Double helix is true. Module is 1.516. Teeth is, what did we come up with? Oh, it's 32 again. Okay, 32. We have our height. Height is 20. Okay, go ahead and calculate that. Okay, and there's our stage 2 planet. Right, so we've got our ring, sun, planet. And now the critical factor is that the planets are offset exactly the same distance between stage 1 and stage 2. So, and that distance is 57.6. So we go over here and we position this at 57.6. And if we look, kind of the same phenomena, the teeth are enmeshed nicely here, out of phase on the sun. So let's just rotate the sun a little bit. There we go. And we should see, yep, those V's are pointing towards the meshing there. And they're pointing away from the meshing here. So we know the teeth are all angled the correct angles. So the gearbox will come together. Now we take this and we are going to move it up. Let's go 22 millimeters up. And we're going to do that on all of these so that when we turn on the first stage, we can see them stacked on top of each other. And we'll see that these two planets, ever so slightly different in sizes, but enmeshed nicely in both of their rings and both of their planets. So all of that looks great. Last thing we want to do is take our S2 planet, copy and paste it. We'll slap another one, or we'll just flip it over to the other side. And we can, have I enraged the, okay, good. Good. Okay, so we pop that there, and then we take another copy, and we're gonna put this at 0 and 57.6 here. And then we'll take this one and make a final copy and make this Y minus 57.6. And that is now a fully functional compound planetary gearbox that's going to give you a ridiculous reduction ratio. There's a lot of free space here, which you might want to actually consume with more planets. So you might re-engineer the tooth counts and stuff to have 5 planets if you're dealing with modules of this size and tooth counts of this size. Make all the tooth counts multiples of 5 instead and do that. But that's the long and short of it, really. So I hope you found this, educational, probably not entertaining, but informative. So thanks for watching. I hope you have a great day. Bye. Thanks for watching. I hope you learned something. I'm Josh Whitman with Whitman Technological. I love science and I hope you do too.